Okay, now let us continue with the class. Today we're going to do a 5.1 and 5.2. All right, magnetic flux, and then we're going to look at some of the applications. So first of all, let us go through the equations in the magnetic flux in 5.1. 5.1, we're going to focus on two equations. The first one is a magnetic flux, which is a phi equals to a B dot A. Now, since you have a dot product, remember, whenever you have a dot product, okay, if you want to calculate the magnitude, you want to calculate the value, then you just rewrite it as, equals to BA cos theta, where the theta is the angles between vector B and vector A. Okay, so this is your B, this is your A. So theta is the angles between vector B and vector A. Remember, it is vector A, but not area. Okay, not A, but vector A. Now, if you look at the names, okay, once you have the magnetic flux, another one is what we call magnetic flux linkage. We have a term linkage right here, okay, where the equation is just N phi, okay, capital letter phi equals to N phi. And one more terms that we have, which also use the term magnetic flux, is magnetic flux density. In which magnetic flux density it represents the B, magnetic field. Okay, so three names, three different terms, they all mean three different things, even though all three of them, they consist of terms, they contain the terms magnetic flux. All right, so be extra careful, okay, be extra careful, because this is where students always got confused. Okay, belajar confused. Okay, apa maksud flux, apa maksud linkage, apa maksud density. All right, they all mean three different things. So make sure you're clear, you know what is a symbol for every single terms, and you know the equations for them. Now let's look at example 1. Example 1, figure above shows a side of flat surface with an area 3 cm squared. Now you have a 3 cm squared. This is not SI unit, remember, you need to change it into meter squared. So this is the area. It's placed in a uniform magnetic field. The plane surface makes an angle 30 degrees with the directions of the magnetic field. Now, if you look at this statement, the plane surface makes an angle 30 degrees with the directions of magnetic field. It tells you the angles between plane and field is 30 degrees. But remember, when it comes to theta, theta is the angles between vector A, okay, vector area, not the plane, okay, not the area, but vector A and vector B. So you want the angles between vector A, all right, not the plane. So if you are given the plane and the field, it makes an angle 30 degrees, meaning that the angles between vector A and vector B is actually 60 degrees. Okay, it is actually 60 degrees. So remember, be extra careful with the angle. Okay, you have angles between plane and field, but in the calculations, what we want is actually the angles between vector A and B. So if the magnetic flux through the surface area, okay, magnetic flux, so meaning that this is a phi. If it says magnetic flux linkage, then you have to use the capital letter phi, all right? So what you have right here is just magnetic flux. So phi is equals to 0.9. This M, it doesn't mean meter, it represents milli, okay, milliweber. So calculate the magnitudes of magnetic field. So straight away, we can solve these equations by using phi equals to BA cos theta, given phi is 0.90 times 10 to the power of negative 3 equals to, well, magnetic field is the unknown. So B times A, now 3 cm squared is 3 times 10 to the power of negative 4 meters squared. And then cos 60 degrees. Rearrange equations, you should obtain B equals to 6.0 Tesla. Okay, 6.0 Tesla. So this question, the things that you have to be careful is the angle. All right, the questions purposely give you the angle between plane and field, but in our calculations, the angles that we're going to use is the angles between vector A and vector B. All right, so I'll give you 1 minute to write it down before we proceed to example 2. Okay, now let's look at example 2. Example 2. A single turns of rectangular coil of side 10 cm by 5 cm. So you are given the dimension. From here, you can then calculate the area. Is placed between north and south pole of a permanent magnet. So you have a north pole on the left-hand side, south pole on the right-hand side, which means the B is from left to right. Okay, this is the directions of your magnetic field, right? Directions of magnetic field. So initially, the plane of the coil is parallel to the magnetic field as shown in figure. So initially, okay, initially, you have a B, okay, from left to right. Okay, this is your magnetic field. So this is your B. According to the questions, the plane, it is parallel to the field. That is what happened. Okay, so this is the plane. So plane is parallel to the magnetic field. And then if the coil, it turns by 90 degrees about its rotation axis and the magnitude of magnetic flux density. So now you have the term magnetic flux density, which represent B. It's 1.5 Tesla. Calculate the change in the magnetic flux through the coil. Change means you are going to find the final value and then minus the initial value. Question asking for change in magnetic flux. Therefore, delta phi equals to phi final minus phi initial. Okay, that is the equation that we're going to use. All right, now if you look at the questions, initial state given, plane is parallel. And then the final state, now let's see what happened. Okay, my B is still from left to right. Okay, B is still from left to right. But according to the question, now it turns 90 degrees. Okay, it turns 90. So initially it's parallel and then it turns 90 degrees. All right, so now what happened is that the plane is perpendicular to the magnetic field. Okay, so we have the plane, but that is not the things that we want, right? What we want is the vector area. So if you look at this question, initial state plane is parallel to B. So vector A is perpendicular to the plane, meaning that vector A at the same time is perpendicular to the magnetic field. Meaning that now you have angle equals to 90 degrees. So your phi initial is equals to BA cos 90 degrees. Well, cos 90, you don't even have to calculate it. It is equals to 0. Okay, 0 Weber. So remember, when you have a cos function, okay, when you have a cos function, if the angle is 90 degrees, then it gives you 0. If the angle is 0 degrees, then it gives you 1. Okay, it gives you 1. So what does it mean? It means if you're going to determine minimum value, then you assume angle is 90 degrees. If you're going to determine maximum value, then angle is 0 degrees. Now let's look at the final state. Final state, once again, vector A is perpendicular to the plane. When vector A is perpendicular to the plane, what happened? Now my A and my B, they are parallel to each other. Okay, vector A and vector B, meaning that the angle is now equals to 0 degrees. So phi final equals to BA cos 0 degrees. B is a non-zero value, 1.5. A given, okay, now you have a 10 cm times 5 cm, which is 0.1 meter times 0.05 meter. Okay, and then cos 0, which give you 1. So you don't have to write it anymore. After that, what are we going to do? Okay, you just calculate the value. Okay, you just calculate the value, which will then give you, yeah, where's my arrow? Okay, which will then give you a value that is equals to 7.5 times 10 to the power of negative 3 Weber. So once you have these two values, you can then calculate the change. Okay, so remember you are not done answering the questions yet, because the question is asking for change in magnetic flux. So delta phi is then equals to, okay, 7.5 times 10 to the power of negative 3 minus 0. You still have to show it even though you know it's 0. Okay, because this is part of the steps, part of the solution. You cannot leave it at phi final and phi initial. Okay, no. Okay, you need to show this step. Even though you know phi final minus phi initial is still going to be equals to phi final, but you need to show the complete step. Okay, so the final answer, 7.5 times 10 to the power of negative 3 Weber. All right. In dalam exam, if you leave it at phi final, then 1 or 2 marks will be deducted. Okay, 1 atau 2 markah. Okay, sometimes this step you will get 1 mark. All right, and then your final answer with correct, you need 1 mark. So if you stop at phi final, now even though the final answer is still 7.5 times 10 to the power of negative 3, but you are not done answering the question, so the marks for final answer will be deducted. Right? So walaupun sama, Anda kena tunjuk. It's very important. Okay, it's very important because question is asking for change. All right. So that is example 2. So now I give you few minutes to write down the solution. Okay, I want you to sketch these two diagrams in your books so that you understand what does it mean by plane is parallel. Okay, initial state, plane is parallel. Okay, plane is parallel to field, to B. So what does it mean? That is what it means. Okay, your first diagram right here. So you have to understand the meaning of plane is parallel to the field. So I give you a few minutes to write it down. I want you to sketch the diagram in your solution in your books as well. Right. Okay. So next we're going to look at example 3. Now, example 3 is a very interesting questions. Okay, why is it interesting? Because it tests whether you understand what does it mean by change in magnetic flux. Okay, what happens when there is a change in magnetic flux? And which case, okay, now we are given three situations. In which situations we'll have an induced EMF. Right, so the three loops wire as shown in figure 1 above, they are all in a regions of a space with uniform magnetic field. So now they are being placed in the same magnetic field. Loop 1 is swinging back and forth as the bob on a simple pendulum. Okay, they are kanan kiri, left right. Okay, so swing back and forth. Loop number 2, it rotates about a vertical axis. Okay, loop number 2 is rotating. Loop number 3, it oscillates vertically on the end of a spring. So what are we going to do now? First of all, let us look at the equations. Okay, so which loop have a magnetic flux that changes with time? So let us look at the equations of magnetic flux. Magnetic flux phi equals to BA cos theta. If you look at this question, now they are all being placed in the uniform magnetic field. Okay, the terms uniform magnetic field means that now you have a constant B. Okay, so B is constant according to the informations given. So if B is constant, meaning that, well, now we can remove it from our questions, okay, from our equations. And the second thing is now you have three loops. They all have a fixed shapes. Okay, they all have a fixed shapes. So they all have a constant A in this motion. So A is also constant. So meaning that the flux won't be affected by B and A. So what is going to happen right here? We want to see what happens to the angle. Okay, that is what we want to check. So let us sketch a diagram. Okay, initially, okay, this is the diagram that we have. So initially, let's see, loop 1, and then the loop 2, and then the loop 3. Okay, loop 3. Okay, now to make it easier, let me think, how am I going to sketch the diagram? I'm going to wash this object. Well, can I wash it like this? Yes, perhaps I can. Okay, so loop 1, initial state. Okay, this is my magnetic field. Okay, I'm going to sketch the magnetic field first. Okay, magnetic field. All this magnetic field, they are out of the page. Okay, they are out of the page. So initially, my coil, they are all being placed like this. Okay, this is the coil. Okay, this is the coil with the plane facing us. Okay, the plane that is perpendicular to the field. If plane is perpendicular to the field, meaning that now your vector E and B, they are parallel to each other. Okay, so try to imagine now you have a plane like this, and then you put a pen on the screen. Okay, kamu letak satu pen, the pen is facing you, pointing towards you. So you will see that pen and the field, they are parallel to each other because now the field is out of the page. So if you put a pen on the screen, okay, bagi dia touch dengan screen, dengan pen menghadap Anda, facing towards you, then you will see that it is actually parallel to the B. So which in this case, what can we say is that the angle is 0 degree in all three cases. Okay, in all three cases, 0 degree. Now, what happened? Let's say after a few seconds. Okay, after a few seconds. Oops. So after few seconds, well, the first case, loop 1 is moving back and forth. It's swinging left and right. So after a few seconds, the diagram that you have, okay, is still the same. Masih sama. Why? Because it's just moving back and forth. Okay, just a swinging. Just swinging. The angles between the plane and the area is still equals to 0 degree. If loop number 2, now loop number 2, according to the question, is rotating. Okay, so this is my field, this is my field, If it's rotate after a few seconds, maybe now it looks like this. Okay, this is the side view. Okay, this is the side view. So you have a side view. Okay, the side of the coil. It's because it's rotating. Okay, it's rotating. So now what happened is that your vector A is going to the right. Just now your vector A is out of the page. But now your vector A is going to the right because it rotates. So in this case, what can we say about the angle is that now the angle is 90 degree. Okay, the angle is 90 degree between the B and the A. Because your B is out of the page and A is going to the right. So now they are perpendicular to each other. Then how about loop 3? Loop 3, your object simply move up and down, okay, without rotating. So what you are seeing is still the same, okay, while the area and the B, okay, the vector A and the vector B, they are still parallel to each other. So in this case, the angle is still equals to 0 degree. Okay, so by looking at this this 6 diagram, okay, by looking at this 6 diagram, what you can say is only loop 2 has magnetic flux that changes with time because the angles keep changing. Okay, because the angles keep changing. For the other two, the angle is fixed. Okay, what happens is that one is moving back and forth, and then another one is moving up and down without rotating. Okay, without rotating. So in these questions, the answer is loop number 2. Okay, loop 2. So how to explain the answer? Right, yeah, loop 2. Okay, because the angles keep changing. Okay, because the angles keep changing. So according to the equations, magnetic flux equals to BA cos theta. Okay, so your phi is proportional to theta. Thus changing in the angle causes the change in magnetic flux. So that is how you answer it. Okay, you start from the equations. Okay, you can actually start from the equations. Okay, kalau kamu nak tulis dalam bentuk equations, what you can write is, okay, phi is equals to BA cos theta, and then phi is proportional to theta. Okay, so as angle changes, flux will change. Okay, therefore loop 2 is the answer. Okay, so this one, because it doesn't say, okay, start from 0 degree. Okay, so as your theta increase, your phi increase. Okay, phi increase. So that is what you can do as well if you don't want to write it in a statement form. Okay, kalau kamu tak nak write in a statement form. Okay, so therefore change, okay, blah blah blah. Okay, this sentence. Okay, this sentence. You put it as your final answer. So that is how you answer it. Okay, you can start from the equation. You follow the 4-step recipe. Ikut 4-step recipe yang saya ajar kamu sebelum ini. Alright, you start from equations, and then you write down the relationship between these two variables, and after that you explain what happened. So because when angles increase from 0 degree to 90 degree, the flux will increase. Okay, the flux changes. Therefore, okay, causes the change in magnetic flux. So answer is loop 2. Okay, answer is loop 2. All right, now I give you a few minutes to write it down. Okay, I want you to sketch the diagram. Okay, you sketch all 6 diagrams right here, and then you write down the answer. Okay, write down both of them so that you can understand what happened. Okay, so you understand what happened. So the black color one, this one is in terms of the equation. It is in equation form, right? This one is in equation form. This one is in a statement form. Okay, this one is in a statement form. All right, so yeah, actually they're quite similar. All right. Okay, so yeah, I give you a few minutes to write it down. Okay, jawapan dalam hitam dengan merah, kamu tengok macam mana kamu nak susun dia. Okay, you can write them down separately, or you can combine them. Okay, you can combine them, or you can write down you can write it down separately. So therefore, kamu isi ini. So answer is loop number 2. Okay, answer is loop number 2. Okay, so now let's look at the next question. So we are done with the first part, magnetic flux. Okay, we have learned how to check whether there's change in magnetic flux or not. So in this chapter, we're going to look at induced EMF. Now, induced EMF, we are going to focus on just one equations. Okay, mainly this one equations. EMF equals to the phi over dt. Now, of course, these equations can then be expanded into a few more equations. Why? Because by looking at these equations, okay, EMF is actually equals to negative. Now, flux final minus flux emission over dt. You're going to look at the change in the flux. Well, again, before that, we have seen what does it mean by the change in flux. There are a few possibilities. Why? Because equations magnetic flux equals to BA cos theta. Okay, you have magnetic flux equals to BA cos theta, meaning that it doesn't matter whether there's a change in B or a change in A or the change in the angles, they will all give you induced EMF. Okay, and of course, there's one more equations where we derive for a single conductor, okay, which is, okay, we have a few equations. The first one is for one conductor, which is EMF equals to BLV sine theta. Excuse me. Okay, BLV sine theta. And then we have a second equation where we use it for change in area, which is a EMF. EMF equals to negative NB dA over dt. And then we have equations EMF equals to negative and AdB over dt. Change in B, change in A. And the last one is a change in angle. Okay, where we have EMF equals to NBA omega sine omega t. Okay, or we can also call it EMF equals to NBA omega sine theta. Okay, sine theta, in which it tells you this equation, this one depends on the change in area, this one depends on the change in the B, and this one depends on the angle. Okay, and the first one is for a straight conductor, okay, where we derive it because there is a change in the area. Okay, this one is for a conductor, a straight wire, okay, a straight conductor. So these three, okay, the other three is for coil. Okay, the other three is for coil. This is a straight conductor, and then this three equation is for coil. Coil, you can have change in area. Okay, this one is because of area. Change in area. This one is because of change in magnetic field. Okay, change in the magnetic field. So you have a magnetic field, okay, field. And this one is because of the change in angle, right? So four equations, but they all came from the same equation, which is EMF equals to d phi over dt, in which we call Faraday's law. Faraday's give you the relationship EMF is proportional to d phi over dt, and Lenz give you this negative. So when you combine the two laws together, it gives you this equation. Okay, give you these equations. So now example 4. Example 4, the magnetic flux passing through a single turns of coil. Okay, a single turns of coil increase quickly but steadily at a rate. So now you have a magnetic flux rate. Okay, magnetic flux rate. So magnetic flux rate, when you're talking about rate of something, okay, especially like the terms rate means that it's being divided by time. So magnetic flux rate, d phi over dt, it is equals to 5.0 times 10 to the power of negative 2 Weber per second. Okay, so the terms the rate itself is very important. So if the coil itself has 500 turns and equals to 500 turns, calculate the magnitudes of the induced EMF of the coil. So induced EMF is equals to negative and d phi over dt. Okay, and d phi over dt. Because now you have more than one turns. If you have just one turns, then n is equals to 1. So which is then equals to, okay, you plug in the value and eventually you should obtain 25 volt. The unit for induced EMF is volt. Okay, same as EMF. EMF kita guna volt, induced EMF pun kita guna volt. So that is the answer for example 4. Okay, so I give you a few minutes to write down the answer and also the summary on the right hand side. Okay, you write down the equations. There's the equations in the 5.2. Okay, but basically if you know what happens, for example, if you know that you are looking at a straight conductor, then obviously that is the only equation for you to use. If you're looking at coil, then you look at what is the variables that have changes in the question. Either the area, the field, or the angles changes, right? So a few minutes for you to write down both the summary and also the answer for example 4.
Madam mute.
Okay, thank you. So now let's look at example 5. Example 5, we have a diagram like this. So a 20 cm long metal rod CD is moved at a speed 25 meter per second across a uniform magnetic field of flux density 250 millipascal. So again, you are given flux density. Flux density is B, and then you are given L equals to 20 cm. Now again, it's given in terms of cm. You need to change it into meter. Okay, you need to convert it into meter. And then V given 25 meter per second across. Okay, now this one is B. So the motions of the rod is perpendicular to the magnetic field. Motion and field perpendicular. Why is it important? Well, because you have equations EMF equals to VLV sine theta. Okay, where theta represents the angles between L and between V and B. Sorry. Okay, between V and B. All right, now let us look at this diagram. Okay, let us look at this diagram. So according to this diagram, you have a B, which is out of the page. That the symbol is out of the page. And then this 25 meter per second, this is your V. Okay, so V and B, that is what we have in the diagram. So calculate the induced EMF, the motional induced EMF in the rod. You have a straight conductor. Straight away, you know that the equation should be EMF equals to VLB sine theta. Okay, VLB sine theta. So it is equals to 250 times 10 to the power of -3. Length is 0.2 meter. Velocity given 25. Sine, now this is the angles between V and B. Okay, angles between V and B. So the angles between V and B, according to the questions, now they are perpendicular. So this is 90 degrees. Therefore, therefore the EMF that you have right here is equals to 1.25 volt. Okay, induced EMF, according to the questions given, is 1.25 volt. Now let's look at questions B. Questions B, it asks you to calculate the induced current if this rod is connected in series to a resistor. Okay, the rod is connected in series to a resistor of resistance 15 ohm. Now, what does it mean? If you look at this diagram, there's no resistor in the diagram. Okay, and remember the things that I told you before, whenever you have a straight conductor, you imagine there's a loop. Okay, if you have just a straight conductor, what is going to happen actually? Kalau kamu cuma ada satu conductor, apa yang akan berlaku? Now, the moment you move it, okay, induced current will be generated. All the electron will move. Okay, all the electron will move toward one end. If it is not a complete loop, then the current will stop quickly. Why? Because now all electrons, they're all accumulated at the same terminal, meaning that no more electron can move. Okay, kalau dia tak ada loop, apa yang akan terjadi? Selepas semua elektron bergerak ke satu hujung, maka tak ada current sudah, dia akan berhenti. Okay, no more induced current. It doesn't matter how you move it, okay, how far you move it. Okay. So in order for it to work properly, you always need to assume, you need to imagine there's a complete loop. And now this question, it tells you this rod is not a complete diagram yet. Okay, it is being connected in series to a resistor. Okay, it's being connected in series to a resistor. So how? So it's up to you whether you want to draw the loop on the left-hand side or on the right-hand side. Okay, remember the things that I told you before? It won't affect your final answer. Okay, it won't affect your final answer. Now let's say I'm going to assume my loop is on the right-hand side. Okay, I'm going to assume my loop is on the right-hand side. So it's being connected in series to a resistor. Okay, in series to a resistor. Okay, I'm going to draw it like this. So resistor. Okay, so this is my resistor, which is equals to 15 ohm. So what is going to happen right here? I'm going to move this conductor. Okay, and now it's being connected to a resistor. So what is the induced current? So the induced current, the current flow in this circuit as you move it, since you have EMF equals to 1.25 volt, so R equals to 15 ohm. Okay, 15 ohm. So when you combine these two, you have I induced equals to, well, remember V equals to IR, so I equals to V over R. So in this case, you have EMF over R. So EMF equals to, first questions right here, 1.25 divided by 15. Okay, 1.25 divided by 15. So your I induced is then equals to 8.33 times 10 to the power of -2 ampere. That is your induced current. Okay, so remember this is actually your induced EMF. Okay, induced EMF. Okay, saya lebih suka tulis subscript. Okay, kalau kamu tengok kebanyakan buku, memang dia tak tulis subscript. Why? Because this chapter is all talking about induced EMF. But when we proceed to a next subtopic, we will have normal EMF and also induced EMF. We will have both EMF in the following subtopic. All right, so for me personally, I like to write this subscript. Okay, for me, I like to write subscript. Okay, now after I determine the values of an induced current, what am I going to do? Let us look at the diagram again. Now, diagram, what happened in this diagram is that you pull the rod to the left-hand side. As you pull the rod to the left-hand side, you're increasing the area. Okay, you're increasing the area. If area increase, it means flux increase. Flux increase, what does it mean? It means B induced will be generated in the same or opposite direction. If flux increase, it means B induced is being generated in the opposite direction. Why? Remember, according to Lenz's law, okay, B induced will be generated in the directions that trying to oppose the changes. Okay, oppose the changes that you insert, you exert, okay, you do on the system. So as you pull the rod to the left-hand side, you are increasing the area. A increase leads to the increase in the flux. Therefore, to maintain its original value, B induced will be generated in the opposite direction. Okay, meaning that it is into the page. So if you have B induced into the page, okay, this is your B induced into the page. By using your right-hand rules, okay, your right-hand grip rules, okay, your B on the right-hand side is into the page. So you let your finger pointing towards the screen into the page, and then you hold the wire, you grip the wire, and you will see that the current is going upward. It's from C to D, from D to C, sorry. Okay, so the direction is from D to C, right? You hold it. You hold it, you will see that your finger is coming out on this side. Okay, fingers coming out on the left-hand side, going into the page on the right-hand side. So when you hold it, okay, you will see that your thumb is going upward. Thumb going up means that the induced current is flowing from D to C. Okay, the induced current. So you determine the directions of induced current by using the directions of induced magnetic field. Okay, kamu guna induced magnetic field untuk determine induced current punya direction. So how to determine it? By using your right-hand grip rule. Just like the notes that I posted in your group just now. Okay, you can go through it. You see how to determine I by using B, or how to use B to determine the directions of I. Right? Now let's look at the questions 2. The total charge, it's asking for total numbers of charge. So what we do know is that the current flowing in this conductor is I induced equals to 8.33 times 10 to the power of -2 ampere. So Q equals to IT. Okay, Q equals to IT. It is asking for total charge. So we are going to determine Q. Okay, this is Q. If it's asking for the numbers of electron, then means that it is asking for N. All right. So Q equals to IT by using induced current from questions 1, 8.33 times 10 to the power of -2 times the time. So what is the time? In 2 minutes. 2 minutes is 120 seconds. Okay, 2 minutes is 120 seconds. So Q is then equals to 10 coulomb. Okay, 10 coulomb. So that is the total charge. Okay, total charge. So that is how we solve questions example 5. Okay, so the part that you have to be extra careful, that you have to take notes, is the questions B. Okay, because you want to know how to determine the direction. Okay, you want to learn, you need to know how to determine the direction of induced current. So that is how you do it. Okay, you form a loop first. So I draw the loop on the right hand side. If you want to draw the loop on the left hand side, go ahead. Okay, nothing's wrong. If you draw the loop on the left hand side, okay, kalau kamu buat loop di sebelah kiri, what is going to happen when you move the conductor towards the left hand side? Here you'll have A decrease. Okay, A decrease leads to flux decrease. Flux decrease means that B induced is in the same direction. Okay, same direction. That's why, okay, that's why I told you just now, if you hold this wire with fingers going into the page on the right hand side, so it must be out of the page on the other side. Okay, it must be out of the page on the other side. So does it make sense? Yes, because if you draw the loop on the left hand side, B induced is in the same direction. Okay, so kanan dengan kiri loop dia tak kisah. Okay, you are still going to get the same answer eventually, which is from D to C. So now I give you a few minutes to write it down. Okay, I want you to write down the diagram as well, to draw the diagram. Now it would be better if you draw down both. Okay, you draw the one loop on the left hand side. Okay, loop on the left hand side, and you make one for loop on the right hand side. Okay, saya bagi kamu masa extra sikit. Saya nak kamu buat dua loop di dalam jawapan Anda, so that you can see. Okay, so that you know it doesn't matter where is the loop, so that you understand the idea. Okay, it doesn't matter whether you draw the loop on the left or on the right. As long as you have the right idea, you have the right concept, then it shouldn't be an issue for you to determine the direction. Okay, so I'll give you more times. I want you to draw the diagram. Okay, for both directions, both loop. Okay, both loop. Okay, so far so good. I hope you can understand. I hope you're still with me, okay, because all these questions, they are just a very fundamental questions. Chapter 5, the idea is quite similar to chapter 4. As long as you're able to identify the type of the object, then it shouldn't be an issue for you to choose the right equations. Okay, dia punya konsep sama macam chapter 4 saja. Kalau kamu tahu objek apa yang kamu tengok, okay, contohnya, if you're looking at conductor, then this is the only equation. If you're looking at coil, and there's a change in area, this is the only equation. Change in field, this is the only equation. Change in angle, this is the only equations. Then once you're able to identify the type of the object and what is happening to them, then you should be able to choose the right equations. Right? So that is example 5. Now let's look at example 6. Example 6. A coil having an area of xcm square. Now you have xcm square again. Remember, cm square is not SI unit. You need to change it into meter square. Okay, meter square. Oops. So this is your area, and then you have a number of turns, which is 50, and it lies perpendicular to the magnetic field. Now, this area, a coil with an area, it lies perpendicular to the magnetic field of 0.2 Tesla. So what does it mean? So this is your magnetic field, let's say. Okay, this is your magnetic field. So your B, the coil is perpendicular. The coil with an area is perpendicular. So this is your coil. Okay, the coil itself, it is perpendicular to the field. Meaning that the vector area is parallel in this case. So what we have right here is theta is equal to 0 degree. According to the information given, according to the statement. Area, okay, the coil having an area that lies perpendicular to the magnetic field. If the magnetic flux density is steadily reduced to 0. So what does it mean? It means this is initial value. Okay, this is initial value. And then this would be a final value. Taking time 0.50 seconds. So determine the initial magnetic flux linkage. So initial magnetic flux linkage, you are looking at initial value, meaning that you're going to use initial B equals to 0.2 Tesla. So a flux linkage, magnetic flux linkage. Now you have the term linkage, means you are looking at capital letter phi. So capital letter phi equals to M phi, which is then equals to N BA cos theta. Okay, so given N is 50, B is 0.20, area 8 times 10 to the power of negative 4, cos 0 degree. So it is then equals to 8.0 times 10 to the power of negative 3 Weber. Okay, 8.0 times 10 to the power of negative 3 Weber. Question number 2 asks you to calculate induced EMF. Now, induced EMF, you have a coil. Okay, you have a coil. And then what happens right here? Now it tells you B changes. Coil and B changes. Obviously, the equations that we're going to use is this one. Okay, these equations. Because now you have a coil with a few changes. So that is what I told you just now. Once you're able to identify the object and what happens to the object, then you should be able to select the right equations. Okay, kamu sepatutnya dapat pilih equations yang betul. Once you know what happens, you're looking at coil, and then what happens to the coil? B changes. Therefore, the equations that we're going to use is EMF equals to negative N A, no, you should have a cos theta, okay, cos theta right here, dB over dt. Okay, just that most of the time we assume theta is equal to 0 degree, which in this case, yes, it is in fact 0 degree. Okay, so if it's 0 degree, then it is equals to 1. So the equation is given above because we derive it by assuming angle is 0 degree. If the angle is not 0 degree, then this is the complete equation. Okay, this is the complete equations. So it is then equals to negative and A B final minus B initial divided by dt, right? Which is then equals to negative 50 8 times 10 to the power of negative 4. B final, well, final it tells you reduce to 0. So 0 minus, okay, 0 minus the initial value, which is 0 0.20, okay, divided by time taken, 0 0.5 seconds. All right. So the answer is then equals to 1.6 times 10 to the power of negative 2V. All right. Induced EMF is equals to 1.6 times 10 to the power of negative 2V. Now, does it make sense? Yes. Okay, does it make sense? Yes. Why? Well, recall the things that I told you before. We have equations EMF equals to negative d phi over dt. If your flux changes, if your flux decreases, then EMF is positive. If your flux increases, then EMF is negative. Okay, this is the things that you need to know because sometimes questions won't tell you whether it is positive or negative, especially when it comes to the induced EMF. You yourself have to be able to determine the sign convention for the induced EMF. So what happens right here? Now I have a B reduced. B initial 0 0.2, B final 0. So B decrease, okay, B decrease means that flux decrease. Flux decrease means that EMF is positive. And yes, I have a positive final answer. Okay, I have a positive final answer. So that is one of the ways that we use to check whether we got the right answer or not. All right, so that is the answer for example 6. So I give you 2 minutes to write it down. Okay, 2 minutes for you to write it down. Again, I want you to sketch the diagram. Okay, because I want you to learn how to visualize the questions. So 2 minutes for you to write it down. All right, so now let's look at example 7. Example 7. A narrow coil of 10 turns and a diameter of 4 cm. So again, you are given N, and then you are given a diameter. This is your D. Okay, but remember, diameter, that is not things that we want. If you want to calculate area, then what you need is the radius. Okay, radius for us to calculate area. So it is placed perpendicular. So again, your coil is perpendicular to the field. All right. So now you have a coil. This is your field. Okay. Again, we have a field. Oops. Okay. Field is a horizontal. Let's assume it's horizontal. So I have a coil that is perpendicular. Okay, a coil that is perpendicular. So once again, if my coil is perpendicular to the field, vector A and B, vector B, okay, vector A and vector B, they form 0 degree between them. All right, 0 degree. So now you have a field that is equal to 1.2 Tesla. So after 0.25 seconds, this is your time, the diameter of the coil is increased to 5.3 cm. So once again, you are given diameter. So now you see, you have 2 diameter. So what happens to diameter? Diameter give you radius and radius give you area. Meaning is that when it comes to example 7, what we have is a questions about coil. Okay. And then in these questions, A changes. Coil and A changes, meaning that we are going to use EMF equals to negative NB dA over dt. That would be the equations. Okay, that would be the equations that we're going to use in example 7. Okay, in example 7. So now let's look at questions A. Questions A, calculate the change in the area. So how to calculate the change in the area? Well, very simple. You just calculate the initials and the final area. Okay, so delta A. Now I'm going to answer the questions. Wait, let me see. Where am I going to put it? Oops. Okay, I'm going to write it. Never mind. I'm going to write it right here. This would be questions A. So delta A equals to A final minus A initial. Okay, A final minus A initial. Now you can either use pi r square, but if you want to keep it as D, also can. Then it will just be pi D initial square over 4 minus pi D final square over 4. Okay, so you plug in the value. Remember to change everything into SI unit because of unit given is in cm. Make sure to convert it into meter. So the final answer should be 9.5 times 10 to the power of -4 meter squared. Okay, that is a question A, the answer for questions A. Now, questions B. Questions B asks you to calculate induced current. But once again, you are given a resistor. Okay, resistance R. You want to calculate I. So obviously, what you need to calculate first is the EMF. Okay, is the EMF. So questions B. EMF equals to negative and B, no, perpendicular. Well, you don't even have to do anything. So dA over dt. Okay, you don't even have to write a cos theta because cos 0 degree give you 1. Okay, cos 0 degree give you 1. So it is then equals to negative 10 and then B given 1.2. Well, dA already calculated right here in the questions A. So 9.5 times 10 to the power of -4 over the times given 0.25. So EMF is negative 4.56 times 10 to the power of negative 2 volt. Now, does it make sense? Let's see. Now, what happens right here? My A increase. A increase leads to change in flux increase. Okay, positive. Your flux increase. Right, flux. It leads to flux increase. When flux increase, EMF is negative. So yes, which is correct. Why? Because now what happens right here? My area increase. Okay, my area increase. Oh, just now I got a mistake right here. This one should be final minus initial. D final, D initial. Okay, so area increase. So area increase leads to the increase in magnetic flux. When magnetic flux increase, we have a negative induced EMF. Okay, the negative sign just means that it's opposite direction. All right. So yeah, that is the EMF. So once I have EMF, I can then calculate induced current. So I induce equals to EMF over R. Right? So plug in the value. Now, when it comes to calculate the values of an induced current, you can ignore the sign. Okay, why? Because this sign, it just shows you the direction. So if you want to calculate current, you can ignore the sign. All right, so 4.56 times 10 to the power of negative 2 divided by 2.4. So current is equals to 1.9 times 10 to the power of negative 2 ampere. Okay, times 10 to the power of negative 2 ampere. So that is the answer for example 7. Okay, that's the answer for example 7. So again, I give you 2 minutes to write it down. Okay, I give you 2 minutes to write it down before we proceed to example 8. Okay, so let's look at example 8. Okay, the last example for this slot, and then we're going to take a short break. So it means that we're going to finish a bit earlier today, and then after that, I'll let you guys off, take a rest. And this afternoon, we're going to continue with example 9 until example 13. And of course, we're going to go through what does it mean by induction first. Okay, both induction process. Okay, now example 8. Example 8, a rectangular coil. So you see, coil is not always a circular coil. Okay, bukan sentiasa coil yang berbentuk bulat. You can have a rectangular coil, you can have a square coil. So make sure you read the questions carefully. So you have a rectangular coil of 100 turns. Okay, this is an N, and has a dimensions. Again, you're given a dimension, which is the area. It rotates at a constant angular velocity. Now, this is your omega, but remember, RPM is not SI unit. What does it mean by RPM? So RPM, if you recall, it means revolutions per minute. Okay, so 1 revolutions per minute. How many revolutions per minute? That is our RPM. In a uniform magnetic flux density of a 5 Tesla, this is your B. Calculate the maximum EMF produced by the coil. Again, question is asking for maximum. All right, now let us analyze this question. Example 8, you have coil. That is the first information that we have. And then what happened? It rotates. What does it mean by rotates? When it rotates, angle changes. So this is a rotating coil questions. Okay, this is a rotating coil questions. So when it comes to a rotating coil, we have EMF equals to NBA omega sine omega t. Okay, most of the time we use omega t. Okay, but if the questions give you angle in terms of degree, then you have to use a sine theta. But omega t means that it should be in radian. All right, kalau kamu guna equations omega t, then it should be in radian. Okay, now according to the questions, you have a maximum EMF. Maximum EMF. Now let's see. We have sine omega t. Sine omega t actually is in the form of sine theta. Okay, a form of sine theta. So when you have sine theta, what does it mean? It is maximum if we assume the sine theta equals to 1. And it is minimum if we say sine theta is equals to 0. All right. So when it comes to this question, when we say it is a maximum value, then this whole thing we assume it is equals to 1. Okay, this whole thing we assume it is equals to 1. All right, now how are we going to solve this question? First of all, let us do a unit conversion. Okay, most of the things, the unit conversion is very simple. Now let's see how to convert the unit for 200 RPM. So omega equals to 200 RPM. What does it mean? It simply means this is 200 revolution per 1 minute. Well, remember, when you have a 1 revolution, it is equals to 2 pi radian. Therefore, in order to convert it into radian, it is then equals to 200 times 2 pi radian divided by 1 time 60 seconds. Therefore, this omega is equals to 20.9 radian per second. So this is what we call SI unit, radian per second. Okay, so now that we have omega in terms of SI unit, we can then solve the questions. So 100, and then this is 5. Now 10 cm by 15 cm, 0.1 times 0.15 SI unit. And then omega is 20.9. So it is then equals to, okay, your EMF maximum. Okay, I'm going to say is the maximum value because I already assume sine omega t is equals to 1. So EMF maximum is then equals to 157 volt. Okay, 157 volt. Questions B. The induced EMF at the instant when the plane, again, if you look at the question, it tells you the plane of the coil makes an angle 38 degrees to the magnetic field. Okay, I'm going to assume my field is from the left to the right again. Okay, and then I have a coil right here. Okay, this is my coil. Now, according to the question, okay, this is a coil. According to the questions, now it tells you the plane. So where is the plane? So this is the plane. Okay, this is the plane. So plane, it makes an angle 38 degrees with the magnetic field. So this is my magnetic field. But that is not the angles that I want. Remember, when it comes to the equations, okay, when it comes to all these equations, the angle is the angle between the vector A, okay, vector A and also your B. So I'm going to draw a vector A first, and vector A. This is my A, okay, vector A. So angles between vector A and magnetic field is here, which is 90 minus 38. So theta, this is theta, equals to 90 degree minus 38 degree, which is equals to 52 degree. So now I can then calculate EMF equals to NBA omega sine. Now this one, I'm not going to use omega t, I'm going to use angle because what I have right now is answer in degree, the angle in degree. So 52 degree. Okay, or I'm going to write out equation first, which in this case, the equation that I'm going to use is the one with theta. Okay, it's the one with theta. So it is then equals to 100 times with the 5, 0.1 times 0.15, omega is 20.9 from previous questions right here. And then sine, 52 degree. So EMF is equals to 124 volt. Okay, 124 volt. So again, for these questions, what I wanted to write down is the diagram. Always sketch the diagram so that you can see what happens, so that you can see where is the angles that you want. Okay, how to determine the angles needed to solve the questions. All right.